Okay, next section. We just got done with the epsilon delta definition of a limit, and now we're talking about continuity. So we have done continuity back in college algebra. We talked about where is a graph continuous, and we had this very scientific definition of it's continuous if you can draw the graph without picking up your pencil, right? We've done that, but now we're going to extend that and maybe get a better definition than there's a break in the graph, so it's not continuous there. Okay, so a lot of times we can find a limit just by plugging in the number. And I've kind of given you some rules for when you can just plug in. I said, if it's a polynomial, we can just plug in the number x is approaching. Well, the reason that is because polynomials are continuous functions. There's no breaks in their graph, and that's why it works. In general, your function is continuous if you can find your limit just by plugging in the number. So it'd be nice to know, if I'm looking at a problem, am I going to be able to plug it in or am I not? And if we can decide if it's continuous, then we could just evaluate the limit by plugging in. The requirements for continuity, it's a three-pronged thing. So this would be the slide that I would highlight and make sure you know. When we look at any of these problems, I'm going to try to decide if something's continuous or not. We're using these three rules. If you tell me something isn't continuous, I'm going to ask you which rule did it break. So, in order to be continuous, the function has to be defined. So you have to be able to plug that number into the function. So if it's a fraction, it gives you 0 on the bottom, that's not continuous. The limit has to exist, and those things have to be equal. The limit has to equal the same thing as when you just plug it in. So to be continuous, the function exists, the limit exists, and those things are equal to one another. In terms of a graph, what we're thinking about is we want to know if there's going to be a break in it. When I'm drawing this, am I going to have to pick up my pencil? Is there an open circle in my graph, or is it a piecewise where the pieces don't match up, or is there an asymptote, that kind of thing. So let's start by looking at a graph. I want to know everywhere this graph is discontinuous and why. And the y has to be one of your three rules. Does the function exist? Does the limit exist? Are they not equal? So can you tell me one value where this graph is not continuous? 1. Okay. Rule number 1 says the function has to exist. Does the function exist at 1? No, it's an open circle. So my reason is f of 1 does not exist. All right, so if I'm drawing this graph, I had a break in it right there at 1. I can continue on. Where's the next break? At 3. Okay, our reasons. Does the function exist at 3? Yes, we have a closed circle. Does the limit exist at 3? No. We have a left-hand limit, we have a right-hand limit, but those aren't the same. So my reason is the limit does not exist. Okay, so I pick up 3 and keep going. Where's the next break in my graph? 5. Does the function exist at 5? Yes, we have a closed circle. Does the limit exist at 5? Yes. When you're coming in from both the left and the right, it is going to the same value. Does the function equal the limit? No. So my reason is f of 5 does not equal or you could just write the function doesn't equal the limit at 5, something like that. So those illustrate the 3 rules of continuity and the problem with each of them. So far, so good? Let's look at another one. All right, I told you to look at the graph, but then I didn't give you a picture of the graph. So let's draw one. All right, where is this function not defined? 2. What's going to happen at 2? What? Yeah, it's going to be an asymptote there because the denominator can't equal 0. Okay, you could use the calculator to help get the graph. We could plug in some points. Let's just graph this on our calculator real quick and get an idea of the graph. So grab one. All you lazy bums sitting and waiting for me to write the answer up here. All right, so if I plug in 1 over x minus 2, what does my graph look like? Owen? What's it look like?
Wait, what?
You were talking, so I assumed you'd already done this, and we're waiting for everyone to catch up.
He's having trouble, so I'll figure it out.
So, 1 over x minus 2, when you graph it, it looks something like this. Okay, so where is this graph discontinuous? Which we already knew. If the function's undefined, at the bottom 0, it's discontinuous there. Why? Which rule is broken? Does the function exist there? Can you plug a 2 in? No. Does the limit exist here? Left and right, do they even match up? From the left, it's going to negative infinity. This way, it's going to positive infinity. So you could technically say any of them. I'm just going to say the function doesn't exist. But it is also true that the limit doesn't exist there. All right, let's look at some more from the graphs. So, graphing a piecewise. You're going to have some on your homework where you might need to graph it. Remember with the piecewise, we did a piece for each section. So we start at 0, and then things greater than that. And what are you getting out every time? Okay, so we have 0, 1, 1, 1, 2, 1. So it just looks like this. Second one, we have to start at 0, but it didn't have an equal to, so that would be open. And then I want things less than that. And what do we get out every time there? Okay, so is the function defined everywhere? Yeah. Where is it not continuous? The function's defined, but what doesn't happen at 0? So what I'm doing is showing you some of the situations where we have issues with our graphs. We have discontinuities. If you have a fraction and the denominator is 0, you're discontinuous. If we have a piecewise, 0 was the breaking point of these two pieces, and we end up being discontinuous there. All right, let's decide if any of these are discontinuous, or where each one is. So A, we shouldn't even have to graph that anymore. We should know where is that going to be discontinuous. And that's because the function does not exist. Anytime you have a fraction, if the bottom's 0, the function doesn't exist there. And it's a discontinuity. Okay, B. Where might we have a problem here? 0. Let's sketch a quick graph and see if we're right. You're on the first one if x doesn't equal 0. So if you put in a 1, get out 1. If you put in a 2, you get 1/4. Put in 1/2, you get 4. The negatives give you the same thing. So there's 1/x². And 1, if x equals 0, that would just be a point on the graph. So you are correct, it's discontinuous at x equals 0. Does the function exist at 0? Yes. Does the limit exist at 0? It does. Both the left and right are going to infinity. So it's that third rule. The value of the function doesn't equal the limit. See. Alright, so normally I'd look at this fraction, which is the same one we had in part A, and the denominator we know can't be 0, but I made it a piecewise, and I'm giving you a point there. So let's work this out. On the top, could we factor and reduce? So that factors in x minus 2, x plus 1. Those cancel and just gives us x plus 1. So if you're graphing, that's just a line, y-intercept of 1, slope of 1. And it's defined everywhere except when x is 2. If you plug a 2 into that, you get 3. So what that is an open circle on your graph. And it exists everywhere else. Then 1, if x equals 2, is just a point on my graph. So is this graph continuous? Where is it not continuous? We'd still have to pick up our pencil there. So at x equals 2. Okay, does the limit exist there? Yes. Does the function exist? Yes. So the reason is the function doesn't equal the limit there. So the graphs can help you on these for sure. D, the greatest integer function. We graphed that one a few days ago. That was just your step function. Remember, it looked like this. Where is that one discontinuous? At every integer, yeah, between those steps. Okay, what's the reason? Does the function exist at the integers? Yeah, there's a closed circle. Does the limit exist? We could do a right-hand limit, we could do a left-hand limit, but do they meet? No, so the overall limit doesn't exist at those pieces. Okay. We've actually just seen a couple different kinds of discontinuities in this. In A and C, these are actually what are called removable discontinuities. Because if we had graphed A, we didn't, but we did it on part C, it was just that line. And so it's removable because the thing creating an issue is just one spot on the graph. And that could be fixed if we just filled in that circle, right? Then it would be continuous. So A and C, those are called removable. We could fix them if, for instance, on part C, it was defined to be 3 when x equals 2. Then that would make that a closed circle on the graph, and then it would have been continuous. In part B, this is what's called an infinite discontinuity, because you have those pieces going to infinity there. You have that asymptote. And the last one is a jump discontinuity. That happens usually with piecewise functions, where you graph one piece and then you have to jump to the next piece. So there's three types. Removable if it's just like an open circle on your graph. Infinite if you have like a vertical asymptote. And jump if you have a piecewise where you're jumping from one piece to the next. It is possible to talk about continuity from the left or the right. So some of these we've said overall they're not continuous, but if you had just went from one side, that would work. So just like we've done limits from the left and right, you could say they're continuous from the left or the right. Okay, so let's look at some, we're just going to spend the rest of class finding out where things are continuous. So this one's a polynomial. Do we have any breaks in our graph anywhere it's undefined? No. So where is this continuous? Everywhere. Negative infinity to positive infinity. That one's always continuous. Okay. Where would this one, where would I have a problem with this one? It's a fraction, what do we have to worry about? So I need to know what would make the bottom equal 0. So this is continuous everywhere except 5/3. That's where it's discontinuous. So it would be from negative infinity to 5/3, union 5/3 to infinity. So if you have a fraction, you don't even really have to draw the graph. You just have to figure out what makes the bottom 0, and it's not going to be continuous there. Okay. What about this one? It's a fraction, so what do I need? I need to know what makes the bottom equal 0. Box method doesn't work. If I did quadratic formula, opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Negative 16 under the radical. If there is a negative under your radical, what kind of number is it? Imaginary. So is this ever going to equal 0? No, only for an imaginary number. So because this is imaginary, that means this will be continuous everywhere. No real number is going to make the bottom 0. X minus 1 over x squared minus 4. What can you do on the bottom? So that factors into x plus 2, x minus 2. So what makes the bottom 0? 2. Negative 2 and positive 2. So that means it's continuous everywhere else. Everything smaller than negative 2. Everything between negative 2 and positive 2. Everything bigger than 2.
On homework like this, do you want us to actually write out the entire?
If I ask you where it's continuous, If it's just one break, then go ahead and give me the interpol. If it's more than one, you could say everywhere except these numbers. That would be fine. Okay, let's do some more. I want to know where this one's discontinuous, and I want to decide if it's removable. In a fraction, when the bottom is 0, you're going to have one of two things happening. Either it's a vertical asymptote, or it's going to be an open circle, a hole in the graph. If you remember from college algebra, you get a hole in the graph when something cancels from the top and the bottom. Now, if we look back at that example 2, when we factored this, that canceled and that made just a hole in the graph. If it doesn't cancel, like on B, that's when you have an asymptote. So if you don't want to draw the full graph, to decide if it's removable, we're asking you if there's a hole. All you need to do is factor and see if anything cancels out. Factor this into x minus 2 and x minus 1. So those cancel. So that means it is removable at 2. So there are 2 points where this graph is discontinuous. When x is 2 and when x is 1. At x equals 2, that is removable because it canceled out. At x equals 1, what kind is that? It's not going to be removable because it didn't cancel. It means you're going to have a vertical asymptote. So is that infinite or jump discontinuity? Infinite. When you have asymptotes, that's infinite discontinuity. If you look at their graph, it's just approaching positive or negative infinity. Is that one okay? Let's look at another one. Okay, in general, anytime I give you something with an absolute value, we have to rewrite it without. So we're going to have our case if, what would be the breaking point? What makes this inside the absolute value equal 0? 1. So we'll have the case if x is greater than 1 and the case when x is less than 1. Can x equal 1 if I'm going to graph this? Can you plug a 1 in there? What would happen on the bottom? A 0. So we can't do when x equals 1. Okay, if x is greater than 1, does the absolute value change anything? No, you're just going to have an x minus 1 on top, x minus 1 cubed on the bottom, and you end up with 1 over x minus 1 squared. If it is less than 1, that means what's inside the absolute value is negative, so when you do the opposite, you would have to put a negative on that, and you end up with negative 1 for x minus 1 squared. All right, so when I write this without the absolute value, I get down to these. Is there anything I can do to cancel that x minus 1 on the bottom? No, it's just a 1 on top. The bottom doesn't cancel out, so that means it is an infinite discontinuity. At positive 1. Because it's still on the bottom of the fraction, so it's still going to be an asymptote. Let's say I wanted to make this continuous. So piecewise functions, they're not continuous when we have those breaks in the graph and the pieces don't match up, right? So I'm going to have a break in my graph at 1. If you plug a 1 into the first piece, you get -1. If you plug in a 1 to the second piece, you get a -4. If I want them to be continuous, I need these pieces to match up. So what should I do to those? I want these to be the same. Set them equal. Add my 4 over. My a has to be 3. So a piecewise function is continuous if your pieces match up at that breaking point. I have one piece left, but I think I'm actually going to save it